Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, episode 3. In this episode, we'll be continuing our discussion on Lewis structures. Let's get started. Now that you've mastered Lewis structures with single bonds, it's time to throw a new concept at you, double and triple bonds. Sometimes, it's necessary for two atoms to share two pairs of electrons, in what's known as a double bond, or three pairs in what's known as a triple bond. When we draw Lewis structures for these molecules, double bonds are represented by two parallel lines between atoms, and triple bonds are represented by, you guessed it, three parallel lines. All the normal rules of Lewis structures still apply in these cases. Atoms can still have no more than an octet of electrons around them. Organic molecules with multiple bonds are fairly easy to recognize. First of all, Lewis structures with only single bonds simply won't work. There won't be enough electrons to complete every atom's octet. Second of all, the names of these molecules will often contain -ene or -n for double bonds, and -ine or -in for triple bonds. This will be further discussed in the nomenclature videos. Let's do a few examples with multiple bonds. First, let's draw the Lewis structure for ethylene, C2H4. We know this will have at least one double bond because the name ends in -ene. The total number of valence electrons in a molecule is not affected by double or triple bonds. We'll count like we normally do. Each carbon has 4 valence electrons, plus 4 hydrogens with 1 valence electron each. This gives us a total of 12 electrons to work with. Similarly, this next step, drawing the molecular skeleton, stays the same. We know that the hydrogens must be on the outside of the carbon atoms, since they can only form one bond each. We end up with this. Now, let's fill in the skeleton with single bonds, like this. This uses up 10 electrons. When we check each atom, we see that both carbons are missing 2 electrons, but we only have 2 electrons left from our total. Luckily, we now know that these electrons can be shared, so we draw them in between the 2 carbons, like this. Now, when we check their octets, we see that all our atoms are satisfied. We did it! Next, let's do ethanoic acid, CH3COOH. Though this doesn't have -ene, we can still tell it has a double bond for a few reasons. 1. Carboxylic acids, by their very definition, must have double bonds. We'll learn more about this when we discuss functional groups. 2. The molecular formula ends in COOH, which is a very big hint. Let's find the total number of valence electrons present. There are 2 carbons with 4 valence electrons each, plus 4 hydrogens with 1 valence electron each, plus 2 oxygen atoms with 6 valence electrons each. This adds up to 24 valence electrons. When we draw the molecular skeleton, we know that there will be 3 hydrogen atoms around the first carbon, because that's what the molecular formula implies. We know that the last hydrogen must go on the outside, because hydrogens can only form one bond. I'm going to put the oxygen to the side of the main branch, like this. When we fill in the skeleton with single bonds, we use up 14 electrons. This means we have 10 left to play around with. Let's try a few different arrangements. First, let's try filling the rest of the octets with just lone pairs. We have to give this top oxygen 3 lone pairs, the carbon below it 1 lone pair, and the other oxygen 2 pairs. This uses up a total of 26 electrons. Too many. We have to do something else. Let's try putting the double bond between the top oxygen and the carbon atom. When we do that, the molecule looks like this. Let's fill in the octets and count electrons. 24. This is the correct Lewis structure. Remember that it's okay to take a few tries to get to the right structure. Many a problem in organic chemistry are solved by trial and error. Let's do a few challenge problems, ones where the molecular formulas aren't written to help us with the molecular skeleton. We'll start with a relatively simple molecule, acetylene, C2H2. We know this is a molecule with multiple bonds because it ends in -ene. In this molecule, there are 2 carbon atoms each contributing 4 valence electrons, plus 2 hydrogen atoms each contributing 1 valence electron, for a total count of 10 valence electrons to work with. When we draw the molecular skeleton, we have to remember that hydrogen atoms always go on the outside. We end up with something looking like this. When we fill in the molecule with single bonds, we use up 6 electrons, with only 4 electrons left over. This is an issue, because each carbon atom still needs 4 more electrons to have a full octet. Luckily, if we stick a triple bond in the middle of the 2 atoms, using up the last 4 electrons available to us, we can satisfy both of them at once. Time for the final problem of this video. Let's draw the Lewis structure for dimethylacetylene, C4H6. The name of this molecule ends with "ene," so we can be confident there's not just single bonds. When we count the total number of electrons available, 4 carbon atoms with 4 valence electrons each, plus 6 hydrogen atoms with 1 valence electron each, we get a sum of 22 electrons. Like with acetylene, we know that the hydrogen atoms must go on the outside. We also know that the molecule will be symmetrical. There won't be 1 hydrogen on one side and 5 on the other side. When we take this into account, we get a molecular skeleton that looks like this. When we fill this in with single bonds, we use up 18 electrons, leaving only 4 to fill the octets of the 2 carbon atoms in the middle. Note that the side carbons have full octets, so we can't add any more electrons to their bonds. After all this practice, you might have already figured out where the rest of the electrons will go, to a triple bond in the center of the molecule. When we check octets, we see that every atom is satisfied. We did it! Let's wrap up this discussion of Lewis structures with a few hints and tricks. Firstly, as I've said before, never be scared to make mistakes. It's okay to find the Lewis structure by trial and error, after some erasing and recounting and redrawing. Secondly, remember that practice makes better. The only way to get better at Lewis structures is to keep drawing them. This will help you become familiar with both the process of drawing Lewis structures and general patterns of organic molecules. I've included a link to a document with some practice problems for anyone who wants to keep going with Lewis structures. Finally, remember that it's okay if you struggle at first. Lewis structures are challenging, especially if you've never been exposed to them before. Even the best, most experienced chemists in the world once battled with Lewis structures, I promise. Don't let difficulties get between you and your chemistry goals. If you have any questions about Lewis structures, feel free to email me or comment down below. The next video will be about formal charge. I'll see you then.